So I'm an irrigation extension officer based at Tatura in northern Victoria. So I work as a part of a team of irrigation officers, and we're based in all of the major irrigation districts across the state. So we work directly with irrigators, looking at their irrigation water management. So do things like whole farm planning, so looking at the layout and how they design their farms, right through to providing irrigation scheduling information. So how much, helping them decide when and how much water they should be applying. And more recently, we've been doing work looking at system checks. So looking at how well their current irrigation systems are operating, and energy efficiency has become an important part of that. So today I'll just go over how we go about measuring and assessing energy efficiency of an irrigation system, and where the opportunities are to actually improve the efficiency of those systems. And I'll touch on a tool that's come out of that, an energy calculator that we have developed, and then we've expanded and created a new prototype, and we're now working with JOC and New South Wales DPI to expand that even further, and hopefully roll that out over a wider area, get better usage of that. But that's in, I guess, a prototype stage at the moment. But it's really aimed at, I guess, helping farmers understand how efficient their system currently is, and whether it's actually worth making any changes to their system, whether the savings are going to pay for themselves, essentially. So as I said, I work in northern Victoria. Traditionally, we mainly have flood irrigation, but we're getting more pressurised irrigation, like these centre pivot irrigators we can see here. I'll just change my pointer. So you can see the distribution of these irrigation systems across the region. So they're going in largely for better productivity and water use efficiency and labour savings, but the downside to these systems is that they have an energy cost associated with them. You've got to pressurise water. And what we're seeing, and it's been seen across the country, that as energy, electricity and diesel prices go up, that the cost of operating the systems actually starts to drive when they use them. So people will start to use them on weekends and at night to take advantage of off-peak power. But I think in a lot of cases, the productivity losses from not irrigating when the crop needs it is probably going to outweigh those the operating cost savings. But I guess what our job is to do is to make sure these systems are as efficient as possible, so that farmers are confident to use them when they need them. So in our assessments, we look at application efficiency and uniformity, so how well they're putting water out, how evenly they're putting water out. And I guess that's about minimising the amount of water that needs to go through the systems. And if you're putting out less water, you're pumping less water, so that's reducing energy costs. But the other side's looking at just how much energy is required for every megalitre of water pumped. And so we assess the energy efficiency to try and reduce the actual energy costs. So just the background for when we're assessing the energy consumption of a pumping system, there's two main components that we actually look at. There's the pumping system efficiency, which is essentially how efficiently the power or diesel is converted into the movement of that water in the pumping system itself. And the second part that we look at is the total operating pressure. So what pressure is that irrigation system actually having to push against to get water through the irrigation system itself? So the pumping system efficiency, if that system's 100% efficient, so there's no energy losses in it, it'll take about 2.7 kilowatt hours of energy to pump 1 million litres of water against 1 metre of pressure. So we use metres as a common measure of pressure. It's equivalent to 10 kilopascals, so I'll talk about metres of pressure quite a bit. But the pumping system is never 100% efficient. We get any efficiency losses in the motor, heat and noise, and so it's important that we get the motor right and that the sizing of that right, and that it's cooled so that it's operating as efficiently as possible. We get efficiency losses in the drive system. Direct shafts are pretty efficient, but if it's a belt-driven system, they can slip and create heat, so there's efficiency losses there. And there can also be efficiency losses in the pump. So there's heat losses in the pump, and also the impeller can spin in the water without moving it if it's not designed right. Most pumps should be ideally will be better than 70% efficient, but it all depends on the design of the system. So the type of pump, the size of the pump, so the size of the inlet and the size of the outlet, the impeller size, all impact on how efficient that pump will actually be. And that system has to be designed to match a particular flow rate and pressure of an irrigation system. And if we change the irrigation system and we change the flow rate and we change the pressure, then the efficiency will change. And it could change to the point where a different pump or a different impeller is actually better suited to the job. So we spent a fair bit of time assessing the system, looking at how it's designed and whether it's appropriate for the irrigation system that it's attached to. We see efficiencies ranging from 80%, which will use about 3.4 kilowatt hours per megalitre per metre head, down to as low as 30% efficient, so using 9 kilowatt hours per megalitre. And that variation is all related to how efficient this part of the system is operating. The second part of what we look at is the irrigation system itself and how much pressure is required to push water through that. So there's pressure required to push water up a hill if there's any hills, not that we've got too many where we are, but there's also pressure required to push water through pipes because of turbulence and friction loss. So in this particular system, to achieve 10 metres of head at the end of the system that irrigation system might require to operate properly, we've actually got to apply 50 metres of pressure at this end. And so we actually multiply that number by the efficiency to work out how much power is actually going to be required to pump that system. So an 80% efficient system pumping against 50 head would use about 170 kilowatt hours per megalitre, whereas a 30% efficient system is going to use over 450 kilowatt hours per megalitre. So that the efficiency of the system is really important. But as we see, if we can change the irrigation system, put bigger pipes on, and reduce the head at the pump required to achieve the pressure at the end, we've halved the head at the pump, we've halved the power requirements of that irrigation system now, without changing the efficiencies of the pump. In reality, it probably would also impact on the efficiency of the pump. But so there's two main areas that we look at: the pumping system efficiency and the irrigation system pressure required. So this is just some data from the assessments that we've actually done, looking at the energy efficiency of systems in the Shepherd and the irrigation region. So here we've got that total pressure that the system's working against, the total dynamic head, ranging from low to pretty high. And this is the energy requirement in kilowatt hours per megalitre. And so ideally, when we change the efficiency of the system, we're pushing points down this way. When we change the total pressure they're operating against, we're pushing them back this way. And ideally, systems will be designed down here, and we work with farmers to try and get them designing systems down here, but that usually means that the capital costs are going to be higher. It's going to be more expensive to set that system up. So we end up with systems here that are a bit cheaper to set up, but the compromise is they're a little bit more expensive to run. Systems up here are always going to be expensive to operate, and ideally we should be trying to try not to produce systems like that, but there's plenty of them out there, and they're the farmers that we spend a bit of time with. So I was just going to show a couple of examples of farmers that we've worked with. Some of these points are the same system, but we've actually made changes to the system. So this particular farmer had a centre pivot, something like this one, operates at a pretty high pressure, and that was basically because it was an old pivot with an end gun on the end of it that didn't have a booster pump. So end guns are usually an add-on. They're a cheap way of extending the length of the pivot and getting some extra land, but because they have to throw the water so far to irrigate, they're very energy intensive. So we encourage farmers not to put them on because they're not very, they don't irrigate very evenly, so they do an ordinary job, and they also cost a lot to run. So this particular farmer had decided to take his off, but because he, at the other end where the pump is, or the pump's at the pump shed over here, because it didn't have any way of reducing the speed of that pump, once he took the end gun off, it didn't actually change the pressure of the system. So we actually got him to put on a whole lot of new nozzles that allowed him to put out more water through that irrigation system, and that dropped the pressure. So that cost about $300, and that dropped the pressure from about 50 meters of head at the pump back to about 42. That's about a $10 a litre saving in pumping. He pumps 300 megalitres a year. So that's $3,000 a year in energy savings on that system, just by having a look at it and changing those nozzles and taking the end gun off. That's $45,000 or over $40,000 over a 15-year period. So a small change to that system can have a big impact on cost. Certainly pay for itself very quickly. And the final system I just wanted to have a look at was this one up here. It was an interesting one, horribly inefficient. It was a very small system, only about 3 hectares. Had a horribly oversized pump and motor and a generator to run the towers to make the wheels turn on the pivot. And so it was using a huge amount of energy per megalitre pumped. But because it was such a small system, he only pumps about 24 megalitres a year through it. We couldn't come up with any changes to that system that was cost effective. He just wasn't using enough water through that system to pay for the changes that he was making. So unfortunately, he's put in this inefficient system. He's sort of stuck with it. He can't justify changing it. So it's really important to get them right at the start, ideally. But it's also important to look at total amount of water that the systems are using to work out how much money is being spent on pumping, and therefore if a change is cost effective or not. So the irrigation energy calculator we're working on, I won't go into it much. I think it's pretty exciting. So to do those calculations that we've done and work out where the savings are is quite, we spent a reasonable amount of time doing measurements in the field, but then a lot of time doing calculations when we get home that the average farmer is not going to do. And so it's really difficult to work out, what the savings are going to be, whether it's worth making changes or not. And so this calculator is a really simple way of working out if there's improvements that can be made, where those improvements need to be made, and what the savings are likely to be. So there's a few extra add-ons on here that I won't go into, but the information that goes into it is really simple. The main things are essentially the length of the pivot, the amount of water that you use per year, so that we add that up over the course of the year and the area and over 15 years to work out how much water they're pumping over the life of the system. We have to put in how many kilowatt hours per megalitre, so the energy use consumption of the system as it is at the moment. And then the only other information they put in is pressures that you can measure on different points on the pivot. So pressures at the pump, pressures at the tower, and at the end of the system, and their regulator ratings. And so this looks at the pumping system efficiency. So this one's 82%. So that just looks at the pressure at the pump and the energy use to work out the efficiency. So this one's quite good, costing $45 a megalitre to pump. But then it looks at pressures at different points and how much head loss is occurring in the system. So over this whole system, they're using almost 47 metres of pressure. Ideally, the optimum that this calculator has worked out for that size system should only be losing 32 metres. So that comes up as a red light that shows that it's losing 16 metres of head pressure between the pump and the pivot. It should only be losing 4 metres. So that could be a filter that's blocked. It could be a constriction in a pipe somewhere that needs to be fixed up, or it could be that this whole pipe's just too small or the flow rate's too high for that pipe. So identifies that there's a big opportunity. Could potentially save up to $4,000 a year by changing something between those 2 points. You've got to go out and work out what that issue is, but at least you know where to look. And then the friction the pressure loss between the pivot and the end of the system on this one's almost 9 meters. It should be 6 meters, so that's not too bad. But it might be something very simple like regulators that are faulty, fairly easy to fix. Could save $800 a year by fixing up that section of the pivot. It also tells you about the pressure at the end of the system. There's 2 psi excess, 2 psi of excess pressure at the end of this system. I'd say that's not a problem. Well, it shows up as green, but that's actually costing $500 a year, that excess pressure at the end of the system. So, might be able to back the system off. But across that whole system, there's potentially $80,000 worth of savings in energy that could be made. So a really quick and simple way of identifying where the issues are and what the savings are likely to be of making changes, so you can compare them to the cost of making the changes. So that's pretty much all I wanted to cover today. Thanks to the team who helped us out in the field, and also Delp, and for me it's the Golden Broken CMA that fund the work that we do.